In class, free body diagrams, problem number 5. So when we draw these free body diagrams, I don't get overly concerned about my artistic ability or lack thereof. I normally do a little bit better than that, because for number 5 it's a ball falling. But the idea is I often just draw a very simple picture, circle, square. I do like to put the mass inside of it. I think it's just kind of a nice placeholder to kind of put it. So for number 5, it says a 2-kilogram ball is falling through the air. There is no air resistance pushing on it. So if we look at what forces are acting on this ball, what forces are acting on this ball? We have the force of gravity, which always is going to point straight towards the center of the earth. Are there any other forces acting on this ball? No, that's it. Okay, so in terms of our free body diagram, it's a pretty straightforward one. To fill in the magnitude of the force, which is just simply the number, force of gravity is what we get when we take the mass of 2 times our gravitational acceleration on Earth. Our force of gravity is going to have a value of 19.6 newtons. So my force of gravity is equal to 19.6 newtons. Now, I do want to include net forces and acceleration. Quickly, at a quick glance, I should say, are my forces balanced or unbalanced? Unbalanced, so is my acceleration 0 or not 0? And F net is 0 or not 0? In which direction are my forces unbalanced? So they're going to be downwards, right? So if my net force is down, what's true about my acceleration? It's also going to be down. So I want to show you where something came from in our last 2 units. So Newton's second law says the sum of all our forces is equal to F net, which is equal to mass times acceleration. So let's start with the acceleration. So if I'm going to sum up all my forces, I can set that equal to mass times acceleration. And when we sum up all of our forces, we add our ups, we subtract our downs, and we set that equal to mass times acceleration. So if we add our ups, which in this case, there aren't any. So I add my ups, I add all the forces that are pointing upwards. There aren't any. I subtract my forces going down. By name, I'm identifying the forces. I'm going to subtract my F of G. And in order to determine the acceleration, we can set that equal to mass times acceleration. Now, if we do a quick substitution here, and instead of saying Fg, if I were to do a substitution and say, well, let's just, instead of calling it Fg, let's say it's minus m times g, which is equal to m times a. Mathematically, how can we simplify that equation? I know the mass. I could plug in 2, right? I could. 2 on the m equals 2 on the left, n equals 2 on the right. But because we have a mass in every single term on both sides of the equation, we can cancel a mass out. And what we get for an acceleration, I get an acceleration that's equal to negative g, which on Earth is negative g, so negative, the opposite of g. G is 9.8, so the acceleration in the y direction is negative 9.8. That's where that free fall acceleration came from. In the absence of air resistance, the only force acting on the ball is gravity. It's going to accelerate down negative 9.8 meters per second. Now Aristotle, going back to that kind of discussion, Aristotle said that the heavier the object, the faster it's going to fall, and Galileo said, no, that's not true, it's independent of the mass. This is mathematically why an object in free fall, at air resistance, the mass is not significant. It doesn't matter because we have no air resistance. Now, where mass does have an impact, if we're dropping like a feather versus a rock, then that mass affects the air resistance and makes that air resistance have an impact on it. But that's where that free fall acceleration comes from. It comes from this. So my acceleration, the y acceleration is negative 9.8 meters per second squared, which is going to be that down. And my net force is 19.6 Newton. My downs are bigger than my ups. And I can either say it's down at 19, or we could say it's negative 19.6 newtons, where this is telling me the direction is down. So either of those is fine. We need to assign a direction, and if you use the negative in the y direction, it's okay. I don't put positive and negatives on my free body diagrams. I use my arrows to represent the directions. But when we're talking about net force and accelerations, that's where that comes in. So any object that's in what we call free fall accelerates down at negative 9.8 meters per second squared. And that's why we've been using that in Unit 1 and Unit 2, is because that is what happens, but it originates from this, is where it actually comes from. Last problem that I'm going to talk about with you today, I want to kind of talk a little bit about some of the background on this one, and then I'm going to give you some time for it. So question number 6 is very similar to number 5, but now I have a 2 kilogram ball that is falling through the air, so it starts the exact same, but this time there is air resistance, and that air resistance is 5 newtons. So, what forces are acting on the 2 kilogram object? Gravity, and gravity always is going to point downwards, and air resistance. Which direction is air resistance going to go? If I'm dropping something through the air, and as it's falling through the air resistance is going to be going up, right? It's a type of friction. It opposes motion. So if you're skydiving, woo, you're falling down, that air resistance is pushing back up. So your air resistance is equal to 5 newtons up. Now, how do we calculate force of gravity? Well, we take force of gravity as mass times gravitational acceleration. It's the exact same mass as before, but I'll show it. F of g is equal to m times g. F of g is equal to 2 times 9.8, which is equal to 19.6 newtons. 19.6 newtons. Are your forces balanced or unbalanced? They're unbalanced. Which direction are they unbalanced? So my forces are bigger down than they are up, which means my object's going to accelerate down. Now to determine this is where we start using Newton's second law and maybe just saying which one's bigger and how much bigger. We start looking more at setting this up. So Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. If I'm going to determine my F net first, what I'm really saying is the sum of all my forces is equal to my F net. On that introduction to forces sheet, I said we add our ups. I have one force going up. I have one up. I subtract my forces going down, and I can set that equal to either F net or MA. Depends on what we're asking you, what you're trying to determine at that moment. So if I say, hey, let's solve for F net first, we can solve this for that. My air resistance is 5. So plus 5, 9 is 19.6, which which is equal to F net. So when we go through and we plus 5 minus 19.6, we get a negative number, which that negative is going to tell us the direction. So this F net is equal to negative 14.6 newtons. My downs are 14.6 newtons bigger than my ups. So this is going to be 14.6 newtons down, or negative 14.6 newtons. Either way is an acceptable way. Now just realize that if you were to write it as 14.6 newtons downward, that if you are going to then use that number in Newton's second law, you need that negative. You're going to need that negative. So how do you determine acceleration? Well, F net, sum of all my forces, is equal to F net, which is equal to mass times acceleration. And now, since we've already determined F net, I can say negative 14.6 is equal to my mass of 2 times A, and A is equal to negative 7.3 meters per second. So negative tells me that direction. So air resistance does have an impact. We don't do a whole lot with air resistance because I mentioned earlier it's a varied rate problem. If you're driving down the road and you at 10 miles per hour and you stick your hand out the window, you feel some of that air resistance. Push your hand back a little bit. You go 35 miles per hour and you stick your hand out the window, it's going to push back a little bit more. You go 55 miles per hour, stick your hand out the window, it's going to push back a little bit more. The faster you go, that higher the air resistance. So that's what we're saying by it's a varied rate. We can't just say, oh, the air resistance is 10, because as you increase your speed, as you accelerate, then what happens is your air resistance increases. So there's a special term that we use for air resistance in like an object in free fall. And the idea is if I were to jump out of a plane, whee, and I'm skydiving, at first, the air resistance is pretty negligible. Like the moment you jump out of the plane, whoa, I'm accelerating downwards at negative 9.8 meters per second squared. But as soon as you start going some speed, there's going to be some air resistance. And you're going to go faster and faster, and the faster you go, because you're accelerating down towards the earth, you're going to go faster and faster and faster. But the faster you go, your weight doesn't change, but your air resistance is going to increase. It's going to increase and it's going to increase. And at some point you're going so fast that your air resistance equals your weight. And what's true about that situation? If your air resistance pointing upwards as you're skydiving, woo, is equal to your weight, your F of G going down, what's true about your forces? They balanced or unbalanced? They're balanced, which means your velocity is constant or changing. Constant because your acceleration is 0. Are you still falling towards Earth? Yeah, you're still skydiving, right? What's the term that they use for that? Where you're no longer accelerating. Anybody know? Maximum velocity, or there's a T word that they use with it sometimes. Terminal velocity. Sometimes they use the term terminal velocity. So it's the idea that even though you are moving and you're still falling towards the Earth, the air resistance is equal to your weight going down. That's where a feather reaches terminal velocity much quicker than rock. Okay? So you can change your air resistance when you're skydiving. You know, if you're going like what they do in all the movies, like woo, like I don't know, arms out, legs out, going flat, that has a different amount of air resistance than if you're going like in a head-first dive. Okay? Your air resistance is going to be different. You're going to have a different terminal velocity. You're going to be moving faster than the person who's flying flat. When you see that in movies, like someone jumps out of a plane and they got to catch that guy, so they kind of go into a tuck dive position. The other person's like, woo, and then they fight and wrestle and steal the one parachute that they had, and someone goes head, hits the ground a little off. But the same thing happens as soon as you pull that parachute. Now you significantly increase your air resistance for a moment. So what happens is now your air resistance is bigger up than it is down, so now your acceleration is up, but you're still falling down, right? You're still moving towards the center of the earth, but you're accelerating, so your velocity is this way, your acceleration is this way. You slow down when you pull a parachute. But as you slow down, your air resistance gets less and less and less, and eventually you reach a new terminal velocity with your parachute open, and then ideally, when you land, you don't break your legs. Right? That's the ultimate. And you live, and you survive. And there's some stories about parachutes not fully opening and all that stuff, hitting tree branches along the way. We'll talk a little bit about that in momentum. But that's kind of the air resistance thing. We don't do a whole lot with it because it gets kind of complicated with the varied rate. It's a calculation in order to do it. So, that's what I want to talk about today. On the opposite side of this are similar questions. I used the in-class as kind of a template to build the practice to learn worksheet. It's the one that has the stars on it. It's not identical, it's similar. My intent is for you to practice free body diagrams. I want you drawing forces. I want you drawing, filling in numbers wherever possible. I want you filling in net forces. And I want you determining accelerations. Now, I said I'm always gonna give you answers for your homework. This one's a little harder to like put a parentheses number next to it, so I have an answer key. I posted the answer key in the assignment in Canvas. So when you submit this, it's only the one side. We did the one side in class. It's the PTL side. That's the part that gets submitted in Canvas. I have a picture of my answer key below the assignment. Like, click here for the PDF. It's on there. Okay, I want you to be checking your work. I want you to be asking questions and saying like, hey, why didn't I get this? What's wrong? What's going on? And I had a lot of good questions on that free body diagram too yesterday. Like, is this right? Because I didn't have answers for you, right? So I do have those as posted in Canvas, and that assignment is due today, tonight. So with the rest of class, that's what I want you working on. 20-ish minutes. Oh, it's actually closer to half hour. So 30 minutes-ish about. Should be a pretty good time. There's 6 problems. They're going to take you some time. That's okay. But work through them. Get stuck. Figure it out. Work through the struggle. That's how we get better at stuff. But this is the building blocks. These are important. Identifying forces, knowing what's going on. That's the start. Okay? So let me know what I can do to help. I'm more than happy to answer questions. Please, please, please ask.